Welcome to Brain Vision.
Now we have a reheat Rankine cycle, but now we have some efficiencies on both of the on the turbine. So the turbine is, and we also have an efficiency on the pump. So the turbine efficiency is 85%. So these lines are not vertical anymore. Okay, so we're increasing entropy as we go through the turbine. And the pump efficiency is 90%. So we're increasing entropy as we go through the pump also. Up here, we have 12.5 megapascals. We are told that we don't want a moisture content of more than 5% here, so that means we have a quality factor of at least 95%. The temperature then was the temperature at 3. We're told is, let's see here, is 550 degrees C. And the steam is then reheated at constant pressure to 450 degrees C. Let's see here. So that would be, is that T4 or T5? That's T5. Yeah, I was going to say that doesn't make sense. So T5. So again, this temperature is a little lower than this temperature. We have mass flow rate of 7.7 kilograms per second. And we have, let's see here, we have what else do we have here? Anything else we need to worry about here? I think not. So we can go and start cranking through the numbers here. So let's see here. We have at 3, we have pressure and temperature. So we can get enthalpy and entropy. And then we know that the isentropic entropy at 4 is the entropy at 3. So that means the isentropic enthalpy at 4 we can get because we know the what do we know? 4 we have or the entropy and the pressure at 4. Did I write down the pressure at 4? Maybe that was the thing that I missed. Yeah, let's see here. Do I have a pressure at 4 in here? No, I think I forgot to write that down. So the pressure at 4 is, what was it? What did they say? 2 megapascals. All right, squeeze it in there. So we have, let's see here, isentropic entropy at 4, pressure at 4, so we can get the isentropic enthalpy at 4. And then we can use the efficiency of the turbine to get the actual enthalpy at 4. And now at 5, we have temperature and we have pressure. This is also P5. Let me put that in here. P5 equals P4. So we have we can get the enthalpy at 5 and the entropy at 5. And then the isentropic entropy at 6, straight down here, is the same as the entropy at 5. And now what we need to do is we need to kind of play around a little bit. This one isn't as easy as previous problems. So we know the actual enthalpy at 5, or at 6, is the enthalpy at 5 minus the efficiency of the turbine times the enthalpy at 5 minus the enthalpy at 6 prime, and the isentropic enthalpy at 6. We don't know, let's see here, what don't we know? We don't know, oh, wait a minute. Yeah, that's why. We don't know the pressure down here. We're not given this low pressure. So we got to figure that out. And so what we can do here is we don't know the pressure at 6, but we know that whatever pressure it is, H6 prime, which would be somewhere here, and H6 are at the same pressure, right? So this, we know H5, we have this. And so what we can do is we know, let's see here, we have at 6, we have the quality factor, and at 6 prime, we have the entropy. So we can play around with P6, until we get a value, a P6 with S. Combine these two to find H6 prime. Combine this and this to find H6, and keep guessing on this until you find a combination that makes this equality true. And when you do that, you'll get 9.73 kilopascals. So again, or you could try to use the software, which is probably the best way to do, even if you are trying to try on error instead of trying to look up a bunch of numbers and tables and stuff. To just use the software and keep guessing, or see if it can. I'm not sure if the software can actually do. Probably can do the root finding for you, or for that, find the proper value by iterating for you. Anyway, once you know the pressure at 6, you know the quality factor at 6, so you can get the enthalpy at 6. And once you know the pressure at 6, you also know the pressure at 1. So now we can get the enthalpy, the saturated liquid here, and the specific volume. And so now we can figure out that the pump, and again using the efficiency, so this times the change in pressure divided by the efficiency of the pump, gives us about 14 kilojoules per kilogram. And then this plus this is the enthalpy at 2. And so now we've worked our way around the whole system, and we have the enthalpy at every point. And so now we can start doing control volumes around things. So control volume around the boiler, we have the the specific heat in is the enthalpy at 3 minus enthalpy at 2 plus the enthalpy of 5 minus the enthalpy of 4 is about 3,600 kilojoules per kilogram. Out, enthalpy here minus enthalpy here. That's 2,270 kilojoules per kilogram about. And so we can figure out the net work is just the difference of these two, and then we can get the power output by taking the net work and multiplying by the mass flow rate, and so we get about 10.2 megawatts. And finally, we can get the efficiency by using the heat transfer. These two, one way, or just W dot net over Qn, or W net over Qn. Anyway, that winds up being about 36.9%.